Alright, so this is going to be the intro video to Calculus 3. Calculus 3 is multivariable calculus. It describes figures in 3D space as opposed to the 2D space learned earlier. So we're used to seeing an XY plane in 2D space represented by two axes perpendicular to one another. So X would go left to right and Y would go vertically. In 3D, we're going to have another axis that's perpendicular to both. So going forwards and backwards, we would have the x-axis with positive x going out of the page. Y would be going left to right with the positive y going towards the right. And z would be going up and down with positive z going up. So from 2 dimension, we would have 4 quadrants labeled 1, 2, 3, and 4. So for quadrants, we would have x and y. Here is 1, 2, 3, and 4. And when they're both positive, that is quadrant 1. And then when y is positive and x is negative, that's quadrant 2. When x and y are both negative, we're in quadrant 3. And when x is positive and y is negative, we're in quadrant 4. So with 3 axes in 3 dimensions, we divide the space up into 8 octants. Now we would have x, y, and z. We'll have 1, 2, 3, 4, 5, 6, 7, and 8. Those are the octants. And similarly, in octant 1, this is when all x, y, and z are all positive. And then octant 2, y and z are positive, and x is negative. And then similarly to the pattern of the quadrants, octant 3 would be x negative, y negative, z positive. And then quadrant 4 is x positive, y negative, and z positive. And quadrants 5 through 8 are when z are negative, and then the pattern repeats. Alright, so now let's compare the 3 dimensions. Let's say we have x equals 2, and we wanted to plot it in these 3 different graphs. So in 1 dimension, it's like a number line. You have 0, and then going to the right, you have 1, 2, and we would just have a point at x equals 2 in 1 dimension. In 2 dimensions, if we're asked to plot x equals 2, we'll still go to the right by 2, 1, 2, and this time we would have a line, since y is unrestricted. And in 3 dimensionals, since y and z are unrestricted, we go forward. X equals 1, here's x equals 2. And we would have a plane in 3 dimensions. In 2 dimensions, the circle formula is x minus x naught squared plus y minus y naught squared equals r squared, in which r is the radius. In 3 dimensions, we can have an equation of a sphere. And this is really similar to the previous equation. This is going to be x minus x naught squared plus y minus y naught squared plus z minus z naught squared. And again, r is the radius, and x naught, y naught, z naught are the coordinates to the center of the sphere. Alright, so let's now do some examples of plotting in 3 dimensions. So let's say we're given x equals 1 and y equals 2. So let's draw our axes, x, y, z, and since x is 1, we'll go forward 1 on the x-axis, and then y is equal to 2, and we have an intersection at 1, 2 right here. However, z is unrestricted, so this is just going to be a line going up and down at x equals 1 and y equals 2. If we're given x squared plus y squared equals 9 and z equals 0, notice that x squared plus y squared equals 9 is in the circle formula. So let's draw our axes first. In the circle equation, the 9 represents r squared, so that means the radius would be 3. So on the xy plane we have a circle, and it goes out 3 here, this is -3, and this is -3. Now this circle is just going to be sitting on the xy plane and not displaced up or down because z is equal to 0. Alright, so if we're given y squared plus z squared equals 4, the radius is going to be the square root of 4, which is 2. And it's y squared plus z squared. We're going to have a circle along the yz plane since x is equal to 0, so we're not moving forward or backwards anyway. 2 to the right is 2, 2 to the left is -2, up 2, and down is -2. So have a circle like this. Okay, so for number 4, x squared plus y squared plus z squared equals 16. So we have a sum of 3 variables squared. So this is the sphere equation. And we have a constant of 16 on the other side. So taking the square root of that, we know that the radius of the sphere is going to equal 4. So to graphically represent this, we can draw 3 circles along each plane. So first with the xy plane, we can go out by 4. Both sides along y, 4 and -4 for the z. So we have a circle along the yz axis. And I'll also do the same for the xy plane, -4. And we're forming a circle along the xy plane. And finally we can represent this along the xz plane as well. So this is usually what is done to represent a sphere in a 3D graph. For number 5, we have x squared plus y minus 1 squared plus z squared equals 4. Now this is also a sphere equation, and this radius is going to be 2. And notice the -1 in the y term. So this means that our center is going to be 0, 1, 0. So this is going to be a sphere with a radius of 2, shifted 1 unit to the right. So here's 1. This is going to be the origin, or the center of the sphere. A maximum of 3 to the right, and -1 right here. And then to label our axes, we still have 2 up, 2 down on the z, -2 and 2 along the x. So let's say we have a restriction at z equals 1. We would go up 1 on the z-axis, and we would be slicing the sphere in a way that we would get a circle. So let's go up 1. We'd be left with the circle. For number 6, z equals y squared with x equals 2. So z equals y squared is a parabola along the zy plane. And then x is equal to 2, so we would have to move forward 2 spaces along the x-axis, and then we would have our parabola. So next we'll be talking about the distance formula. In 2 dimensions, you may be familiar with the equation that was derived from the Pythagorean theorem. In 3-dimensional, it's pretty similar. This time with third point, d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So let's say we wanted to find the distance between 2 points, 2, 1, 1 and 4, 3, -1. It doesn't matter what we want to label as our first point or second point. Let's just call this our first, and call this our second. You'll still get the same answer. So let's use the equation. x2 would be 4, and subtract by x1, which would be 2, square plus y2 would be 3, and y1 would be 1. 3 minus 1 squared, plus z2 would be negative 1, and z1 is a 1. So solving this would have 2 squared plus 2 squared plus 2 squared. This equals the square root of 12. So the distance between those 2 points is approximately 3.46 units. We can also graph this. Our first point is 2, 1, 1. So let's start off with the x and y. So we'll go 2 forward, and then y is 1 to the right. So connecting these would be around here. And z is 1, so we'd go up 1 unit. And this would be point 1, which is 2, 1, 1. And then the second point is 4, 3, negative 1. So we would go forward 2 more. This x equals 4. And then 2 more to the right to get y equals 3 right here. And let's connect these. And then from here we'd go 1 down for z's negative 1. And this would be our second point. And then the distance between these is square root of 12, or 3.46 units.